Welcome. As promised, this is the second part of the video where we're trying to help students understand how the angle of inclination makes its appearance in the context of a free body diagram where you're dealing with an object that's on an incline. So most students, as I've had a chat with, they understand somehow that this angle must appear here, but they're not comfortable as to why. You may have seen possibly lecturers or teachers just putting the angle here in such a situation where you have an incline. But then let's go ahead and actually give you the confidence as to how this angle shows up. The first video was more of an intuitive approach. If that is not satisfactory to you, here's an approach where you can actually navigate using an analytical approach. Okay, so before we do that, let's recap a couple of things. The first one is that our coordinate system has what we call Cartesian coordinates, and by definition, Cartesian coordinates, that is the x-coordinate and the y-coordinate, are separated by an angle of 90 degrees. That is critical. So when you have Cartesian coordinates, the angle between them is 90 degrees. So the angle between the horizontal line and the vertical line is exactly 90 degrees. So that's an obvious fact, but it's useful for us to review. The second fact that we're going to need is a property from Euclidean geometry. That is, if you have two intersecting lines, there are angles, these angles here that are indicated by the blue lines, these two angles are equal. They are vertically opposite. These ones are opposite angles, except now they're in a horizontal side of the, they're also still opposite. So the point is, this angle here is the same as that angle, and this angle there is the same as that angle. You could think of a pair of scissors, right? If you know how wide the two sides are open, you know how wide the other cutting end is open. So that's vertically opposite angles. They're equal. That's just a fact in Euclidean geometry. And then the last fact we're going to need is that an intersector of two parallel lines always produces equal corresponding angles. These two angles are equal because this line is intersecting two parallel lines. Again, this is 2D Euclidean geometry. This is something we learned in high school. Now we're going to invoke all these three facts in the context of a free body diagram, and that will enable us to understand where that angle of inclination should reside in our free body diagram. Okay, so over here I have a blue coordinate system, which is the one that's tilted relative to the horizontal. And there's also the red one, which is upright. That is, it's what you would use when you are dealing with a horizontal coordinate system, or an upright, when you are applying an upright coordinate system. Okay, now let's consider. Consider this red line here and this white line. The white line represents our ground, and the red line represents a parallel line to that. Now, notice we have this red line being parallel to that, but that line is being intersected by this white line, which is the line of our incline. Now, notice we have two parallel lines, and they are intersected by something. So what fact could we use? We could use this fact that since these two are parallel, and they're both intersected by this line, this angle theta must be equal to that angle there. So I am going to go ahead and put it in, and let's maybe use a different color. Let's try green. So I could say that angle there is theta. I hope that's clear to you that that angle is theta. Why? It's theta because you have two parallel lines being intersected by the same common line, so that will produce equal corresponding angles. So that is theta and that is theta. I hope that is clear. And remember, the blue line is also parallel to this white line, which is the line of the incline. Notice these two parallel lines are being intersected by a red line. Do you see that? So this blue line, maybe let me let that fade away. This blue line is parallel to that white line, but both of them are intersected by this red line. So what can you say about that angle there? Then we could happily say that this angle is also going to be theta. I hope you see that. Two parallel lines intersected by one, same common line, producing same corresponding angles. Okay, if you are happy about that, we are about one step away from our desired goal. Okay, now we know something about this vertical line, the red vertical line, and the horizontal vertical line. They are essentially a coordinate system, and that means the angle between them. This angle between them must be 90 degrees. But notice, if this entire angle is 90 degrees, and part of it is theta, what does that tell us about this angle here? So, this entire angle is 90 degrees, but this whole angle is made up of, there's a part of it which we know already, and that's theta. So the remaining part of it must be 90 minus theta. So I'm going to go ahead and put it in there and say that angle, the separation between this red and the blue, this is going to be 90 minus theta. I hope you are still with me. If it's unclear, you feel free to make a comment. I'm happy to clarify or make a subsequent video that would assist. Now we know the angle between this horizontal red line and this blue line. But we have to reinvoke the same fact again about the blue line and that blue line. So this blue line served as our y-coordinate in the tilted frame of reference, and this one served as our x-coordinate in the tilted frame of reference. So what is the angle between this blue line and this blue line? Well, since these are essentially our y and x, except in the tilted coordinate system, we know that the angle between this blue line and that blue line must be 90 degrees, because that's what, by definition, that's the angle of separation between coordinates in a coordinate system, at least in a Cartesian coordinate system. So this is perpendicular to that, making this entire angle 90. But what did we just learn in the previous a few seconds ago? We learned that this angle here is 90 minus theta. This angle forms part of the blue of this 90. So we can say whatever this angle is plus this, that should give us 90. Actually, I'm going to do a bit of an audible here and work it out. Suppose I were to call this angle over here alpha. Let's suppose this angle I were to give it a name alpha. We know that the blue line, this blue line and that blue line are separated by an angle of 90. So let's go ahead and say that angle is equal to 90. But what is that 90 made up of? Well, that 90 is made up of alpha plus this bit, which is 90 minus theta. So we could say that 90 degrees between the blue lines is made up of alpha. Oops, let me stick to the white color. Alpha plus 90 minus theta. And now if we try to resolve for what alpha is, notice when we take this 90 to the other side, it becomes a negative, which means the 90s are going to cancel out. But then when we take the theta to the other side, what will remain is that alpha is equal to theta, indicating that actually this angle here is just theta. Now, one fact remains for us to invoke. Notice, two lines are intersecting. One side of our scissors has an opening of theta. What should be the opening on the other side of our pair of scissors? Well, this is just the good old vertical angles. They're vertically opposite. So if this one is theta, which we just proved over here, that angle must necessarily also be theta. Let's see this in the context of a free body diagram. Well, in the free body diagram, by the same argument, and this is just going to be a repetition, I think this time around I want to show it to you with a little bit less clutter. We have a horizontal line and a horizontal line being intersected by a common straight line. That line makes a theta, angle of theta with one of the lines. Well, it must also make the same theta with the other one. So we could say that's theta, or theta, depending on your, anyway, that's good enough. Now, if this angle is theta, we know that this theta is part of this angle here. What is the angle between the vertical red and the horizontal red? Well, that's 90. If that is 90, but part of it is already theta, in other words, this is already theta, we know this angle is theta. That means this angle up here, which I will write in this gold and yellowy color, this must be 90 minus theta. But then, let's consider what is the angle between this horizontal blue line and this one, the normal force. In other words, what is this angle here? I hope by now you should be able to comfortably deduce that this angle here, which I will label with a, let's go purple, this angle here must also be theta. And if that angle is theta, what should this angle be? That angle must also be theta. I hope now you are comfortable with why it is that why we put the angle theta, the angle of the incline, why do we put it here and not anywhere else? It has to do with that geometric argument using those three properties of Euclidean geometry. I hope this helps. If not, please put your questions in the comment section and I'll hopefully get back to you. Okay, see you in the next one.